This is question number 46 in Giancoli chapter 4. The textbook reads for this problem, for the system of figure 4-32 in example 420, how large a mass would box A have to prevent any motion from occurring if the coefficient of static friction is 0.30? So I've kind of made a sketch of that figure there on the board, and the only thing that we know is that the coefficient of static friction is 0.30. We can see here from the sketch that block B is falling, block A is being pushed horizontally, or I should say pulled horizontally to the right across the table. In these types of question, it's important for us to define a coordinate system. We expect the system to have a tendency to rotate in this particular direction. This would be the clockwise direction. So technically speaking, although you can get away with not doing this, we have to recognize this is actually a 1D problem. So the entire system kind of moves in this direction, even though it's moving in two directions, both the positive x and the negative y. It can only move along that green line. I'm ultimately going to kind of draw two free body diagrams and have two separate dynamics equations describing each. Let me explain. So let's go ahead and start with box A. We should recognize that there are two forces acting in the horizontal direction. There's the tension in the line, F sub t, pulling it to the right, and there's the frictional force pulling to the left. We will recognize that these are going to be equal to each other if it's not moving. Of course, there's also the weight, mg, and the normal force, F sub n. That's for block A. The free body diagram for block B looks like this. We have block B here, and the forces acting on it are weight in the downward direction, mg, and the F sub t, the force of tension in this particular line right here in the upwards direction. So since the system isn't moving, they want to know what the maximum size that block B can be. So I'm going to write some equations for block B in the vertical direction. I can say that the sum of the forces in the y direction for block B are going to be equal to 0. So therefore, I'm going to write now, I have to be careful here. Here's where my sign convention comes into play. And again, I'm being technical here, but negative Ft is equal to positive mg. Or kind of maybe a better way of writing this would be by saying that mg, which is now positive, minus Ft is equal to 0. And the reason that I said that was because, again, anything that's moving the system in this clockwise direction, so in this direction is going to be positive, and moving in the opposite direction this way is going to be negative. And so the weight then is in this downward or clockwise direction, attempting to rotate the system that way, so we'll call it positive. At the end of the day, I end up getting an expression that simply is going to be mg is equal to the force of tension in the cable. Now, let's take a look at the A box. I can also say that the sum of the forces, in this case, in the x direction, are equal to 0. And I can say that the tension minus the frictional force is equal to 0. And again, I can say now that the tension in the cable is equal to the frictional force. The frictional force is ultimately known. I know the coefficient of static friction that was given to me in the problem, and I could figure out the normal force by looking at these forces here. So the frictional force is known, and therefore I ought to be able to figure out the tension here. So I could figure out the tension, and once I know the tension here, I could figure out the weight. There's a little bit more of an elegant way of doing this, though. We could recognize that it's a system of equations, and I have the force of tension resolved in both cases, block A and block B. I could set these equal to each other. I could set this one here equal to this one over here, and so ultimately I'm going to be left with the force of friction, which is equal to Ft, is equal to the tension in the other direction for block B is going to be equal to mg. And I need to now put some subscripts here. That's going to be the force of friction on block A is going to be the weight of block B, mg, for block B. Now I can separate this up and say, okay, well, this is going to be the coefficient of static friction times the normal force is equal to the mass of block B times the acceleration due to gravity g. And finally, the normal force on block A is going to be equal to the weight mg. In order to do this formally, I would need to say that the sum of the forces in the y direction on this block A are equal to 0. And therefore, the normal force minus mg is equal to 0. And therefore, the normal force is equal to mg. This is for block A, of course. So now I can take this expression for normal force and substitute it in here. And I'm going to be left with mu static times the mass of block A times g is equal to the mass of block B times g. I'm ultimately trying to solve for, in this particular case, I'm trying to solve for the mass of block A. I guess I had kind of initially confused that. And in that figure, the mass of block B is given to me as 2 kilograms. So there is an additional piece of information. I do know the mass of block B. So I'm ultimately solving for the mass of block A here. Okay, so now I'm going to rearrange this equation and solve for the mass of block A. I'm going to divide both sides by g. And therefore, I'm left with the mass of block A is equal to the mass of block B divided by this coefficient of static friction. And when I do that, the mass of block B is 2 kilograms. And the coefficient of static friction is given to me in the problem as 0.30. 2 divided by 0.30 for problem number 46 is going to give me 6.7 kilograms. And 6.7 kilograms then is the solution to problem number 46.